Good morning, class. Welcome to this lesson on Circuits 10, Parallel Circuits. Today we will be able to solve for current, resistance, voltage, and power in a parallel circuit. So a parallel circuit, by contrast, I put a parallel circuit right here next to a series circuit. Remember, a series circuit has one continuous pathway. So this is series down here, so there's one pathway. In a parallel circuit, we can see from this diagram right here, there are multiple pathways. Multiple pathways. So as you can see, we have the battery and it's going around, and at this point it branches off into three different paths. And so that's how we mean by parallel circuit. And these pathways, like in this diagram, are parallel to one another. That's why it's called a parallel circuit. So a parallel circuit means multiple pathways. A single circuit means single pathway. The benefit of a parallel circuit is this, is that if one of the pathways is turned off, like if this light bulb is turned off right here, these two will stay on. As opposed to in a series circuit, if we cut off the current right here, for example, the entire thing turns off. Kind of like Christmas lights. If you ever had that problem with one light going out and killing the whole strand, that's a series circuit. Once you disconnect it at one point, you lose the whole thing. So a parallel circuit has multiple pathways, and each pathway has its own power, own current. So if you cut off one, you don't cut off all the rest of them. Okay, so that's a parallel circuit. So we have 5 rules for parallel circuits. I'm going to do an example as I do the rules, and then I'm going to do another example at the end to just bring the point home. So here we go. First rule, each device connects the same 2 points, between the same 2 points, A and B, okay, of a circuit. Therefore, the voltage is the same across each device. What it means by A and B, it's talking about A and B right here, okay? So each device is connected between the same 2 points, A and B, and so the voltage is the same across each device. In this picture right here, A and B would be like this, A and B. So each device is connected between A and B. And so this makes it kind of nice. If I have a battery right here, this is my battery, and let's just say, for example, that this battery is 36 volts, okay? What it's telling me is that the voltage through this resistor is 36 volts. The voltage through this resistor is 36 volts. It is going to be the same potential difference across each device. Whereas before, in series circuits, we had to add them together. Okay, so this is going to be the same potential difference across each device. So that's very easy to calculate. Okay, as branches increase, current increases. Therefore, total resistance decreases. Overall, the total resistance is less than the resistance of any one branch. Okay, so let's take a look at this example right here. I have 20 ohms and 30 ohms. My formula for solving for total resistance or equivalent resistance, remember those are kind of like the same thing, is going to be 1 over R equivalent equals 1 over R1 plus 1 over R2, etc. Okay? So in this example, it's going to be 1 over R EQ equals 1 over 20 plus 1 over 30. I'm using the 2 resistors right here. Okay? So these are fractions. We have to add fractions together. We need a common denominator. Common denominator 20 and 30 is 60. 20 goes into 63 times. 30 goes into 62 times. So we get 1 over REQ equals 5 over 60. And notice this is the reciprocal, so we have to flip it. So the equivalent resistance is going to equal to 60 over 5 or 12 ohms. Notice my answer is going to be less than any individual resistor. So this is 20 and 30. My answer is less than both 20 and 30. Okay. So when we add more circuits, when we add more devices in a parallel circuit, overall resistance decreases. As opposed to a series circuit, if we add more devices in series, resistance increases. Okay. So no matter what, if you had an example with a 4 ohm resistor and a 6 ohm resistor, for example, we know the overall resistance is probably going to be like 2 or 3. It has to be less than 4 and 6. Okay, it has to be less than 4 and 6. So the overall is going to be less. So let's erase that. So that's how you solve for resistance, equivalent resistance in a parallel circuit. Okay? The total current of the circuit divides among the parallel branches. Ohm's law applies to each branch when solving for current. Okay, so let's go back to our example here. We have 36 volts here. We have 36 volts here. Okay, we're going to use Ohm's law for each branch. So V equals I times R, and we're trying to solve for current. Okay? So let's do total current first. The total current is going to be equal to V over R. So V total right here is 36 volts. 36 volts, and the equivalent resistance of the whole thing, remember, was 12 ohms. So my total current is 3 amps. Okay? That's total current. If I want to know the current in each branch, I'm going to do the same thing. I equals V over R. The voltage is the same. That makes it easy. 36 volts over 20 ohms. 36 volts over 30 ohms. If I calculate this out, I get 1.8 amps. If I calculate this out, I get 1.2 amps. Okay, so the current going through right here is 1.8 amps. The current going through right here is 1.2 amps. Notice this. If I add 1.8 and 1.2 together, I get my total current. That's what this piece is saying right here. Total current of the circuit divides among the parallel branches. Ohm's law applies to each branch. Okay, so we use Ohm's law to find the current in each branch. The current is not the same, unlike a series circuit. In a series circuit, they're the same. Okay? Rule number 4, the total current equals the sum of the currents in parallel branches. That's what we just did right there. 1.2 amps plus 1.8 amps equals the total 3 amps. Okay, last, the power delivered to each device added up equals to the total power for the equivalent resistance. This is the same as we learned before in the first video on series circuits. Okay, same thing. So in this example right here, let's do our power equation. So power is going to equal, we'll do the equivalent resistance. So we're going to use I squared R. I squared, this is 3 amps, so this is going to be 9 squared times our equivalent resistance, which is 12 ohms. And so we get from this, we get 972 watts. 972 watts. Now, if I did it for each resistor right here, each resistor, why don't we do P equals I times V? I times V. Hold on, before I move on, I made a big mistake right here. I squared, I is 3 squared, and so my total is 9. I did 9 squared on accident. So 9 times 12 is not 972. 9 times 12 is 108. That's a big difference. Sorry about that. Okay, so this is my total current. This is my total resistance. I get 108 watts. So let's do P equals I times V for each resistor. The current through the first resistor was 1.8 amps, and we have 36 volts. For the second resistor was 1.2 amps times 36 volts, and so 1.8 times 36 is equal to 64.8 watts, and then 1.2 times 36 is equal to 43.2 watts, and if we add these two together, we get our total power. So that was one example. I'm going to do another one a little bit bigger just to re-emphasize the same point. We're going to have a parallel circuit here with 3 resistors, okay? We're going to have a 40 volt battery. We're going to have resistor 1 is equal to 5 ohms, resistor 2 is going to be equal to 20 ohms, and resistor 3 is going to be equal to 4 ohms. Okay, and so let's label everything we're going to solve for. We're going to find equivalent resistance. We're going to find total current. We're going to find total power. We're going to find the voltages for each one. We're going to find the current through each one. And we're going to find the power through each one. Okay, let's start with equivalent resistance. Equivalent resistance is going to be 1 over R EQ equals 1 over 5 plus 1 over 4 plus 1 over 20. The common denominator here is 20, so 1 over R EQ equals something over 20. 5 goes in the 20 4 times, 4 goes in the 20 5 times, 20 goes in the 20 1 time, so we get 10 over 20. We're going to flip this because we need to find the reciprocal. So our total resistance here, our equivalent resistance is 2 ohms. So we have 2 ohms right here. Okay, Our total current is going to be equal to voltage over total resistance or equivalent resistance. So our voltage here is 40 volts. Our equivalent resistance is 2 ohms. So we get a total current of 20 amps. Okay, these three are very, very simple because the voltage through each one is going to be the same. So these are all going to be 40 volts. These are all going to be 40 volts. Now we need to find current for each one. Current is going to equal V over R for each one. And so it's going to be 40 volts divided by 5 right here. 40 volts divided by 5, that's going to be 8 amps. 40 volts divided by 20, which is going to be 2 amps, and then 40 volts divided by 4, which is going to be 10 amps. Notice all three of these add up to that amount. Current is divided in each branch, okay? Current is divided in each branch. Let me erase some of this. And for this one, we'll do power is equal to V squared over R. V squared is going to be 40 squared over our equivalent resistance of 2 ohms. And for this, we get 800 watts. This is 1600. 40 squared, 600 divided by 2 is 800 watts. So we're going to have 800 watts right here. Let's now solve for the power in each one of these. We'll do the same thing as last time. We'll do P equals I times V. Okay? The current through device 1 is equal to 8 amps times the voltage of 40 volts. For 2, it's equal to, excuse me. Okay, P2 is going to equal 2 amps times 40 volts, and P3 is going to equal 10 amps times 40 volts. 8 times 40 is 320. 2 times 40 is 80. And 10 times 40 is 400 watts. Notice 320 plus 80 is 400. 400 plus 400 is 800. The total power adds up there. So that is a big example in how to solve for a current, resistance, voltage, and power in a parallel circuit. I highly recommend, because we're going to get into combination circuits next. Our combination circuits, we're going to combine parallel and series. You need to be very familiar with these rules or else it's going to get very confusing. So practice.